Okay, let me welcome you to this 12th lecture of our course in reinforcement learning at ASU. And today's lecture is devoted to aggregation. Now, aggregation is just another offline training method. It's offline. So it produces a cost function approximation. Sometimes it may produce a policy that are used for online play, for whatever scheme you may have for online play. Now, the difference between aggregation and some of the earlier ideas that we've discussed for offline training with neural networks and other approximation architectures is that the training ideas are quite different. And they are based instead of cost function approximations from samples. They're based instead on problem approximation. We approximate a problem, and then through the problem, we obtain approximating cost functions. And the ideas are also related to discretization ideas that are common in other fields of numerical analysis as well. So today's lecture is going to be based almost exclusively on videos from previous lectures, and also the earlier courses of the 2019 version and last year's version had more material on aggregation. In particular, the 2019 course had 2 lectures on aggregation. So today's lecture is a little bit of a condensation of the earlier treatment of the subject. And if you want to see more details, you can refer to the earlier versions of the aggregation lectures, particularly the one of 2019. So what I'm going to do now is get into the video. We're going to have some introductory remarks to aggregation, its nature, and what we can expect from it. Then we are going to talk about a simple form of aggregation that involves representative states. I'll explain what that is. It's a form of discretization of the state space with a coarser grid than what there might have been there to start with. Then the basic principles of aggregation for representative states are going to be extended to a more general type of aggregation involving features. And we're going to give a number of examples of this type. We're going to form an aggregate problem, a simpler problem than the one that we started from. And we're going to look at solution methods based, for example, on policy iteration. And also simulation. Then we're going to discuss some variations of aggregation, and that will be the last topic. Now, most of our lecture, almost all, is going to be based on videos from the 2019 class offering. So I'm going to switch to the video, but at strategic points, I'm going to be pausing for you to ask questions. So let me go to the video now. Start it now. So, where does aggregation fit in the big picture? Well, we have our friend here, the big picture figure, and here's aggregation. Remember, this is for one step look ahead. We're looking at a discounted problem. We're going to be looking at discounted problems exclusively in this lecture. And we're looking at one step look ahead. And J tilde is the approximation of the future costs. And it can be obtained with any of a number of methods: problem approximation, rollout, approximate policy iteration, parametric approximation, neural networks. And we have covered all this. And now we're going to talk about aggregation. There are also the other approximations, but we're going to focus on this. How do we approximate using the aggregation method? So now aggregation is actually a form of problem approximation. It qualifies as a special case of this, if you will. Basically, we approximate our dynamic programming problem with a smaller and easier, less dimensional version. We solve it optimally, and we obtain J tilde in this way. It is also related to parametric approximation because we are going to see that it produces J tildes that can be viewed as feature-based approximations. In particular, if J tilde, we're going to see a major special case. Major special cases are going to be obtained when J tilde is piecewise constant. And we have seen that piecewise constant functions can be viewed as feature-based approximations with the features being 0, 1 membership functions, 1 over a subset, 0 everywhere else. So there is a relation of aggregation with this, there is a relation with this, and not only there is a relation of parametric approximation, but it can be combined with parametric approximation, like a neural network, for example, in 2 ways. We can use the neural network to provide features for feature-based aggregation, or we can add a local parametric correction to J tilde, like a piecewise constant approximation, to a J tilde obtained by a neural network. So we may have already some J tilde obtained from a neural network, and then we can correct it with piecewise constant approximations. Moreover, there are several versions of aggregation. Here's one-step look ahead. We could be looking at multi-step look ahead, which is very similar, finite horizon as opposed to infinite horizon, and there are other versions that I'm going to go into in the next lecture. For today's lectures, this is the figure, okay? Okay, so let me get across this idea through a simple example, which dates back to the early days of dynamic programming, approximating a state space which may be large with a coarse grid of states. In fact, it's an idea that goes back to the very early days of computation, okay? Any kind of numerical computation has at some level involved ideas like that, sort of thinning out the number of variables and focusing on a certain subset. So here, the states in this figure are the cross points on this grid, the black cross points, okay? And they are represented by they are represented by this fine grid. The representative states are the red ones, okay? It's a smaller subset. And so this is, the red grid is a coarse grid that lies in between the fine grid. And we introduce these states, and we call them representative. Okay. So now, the idea here is to approximate the original dynamic programming with a coarse grid dynamic programming problem, whose states are these fewer red dots. To do this, we have to form an aggregate problem, and for this we need transition probabilities from red states to red states. How do we move under the influence of control? In order to define an aggregate problem, we need to define transition probabilities, and we need to define also the cost of transition from red states to red states. Now, suppose we have done that, we can solve the aggregate problem by exact dynamic programming. Because there are fewer representative states, we may consider doing that. Now, after we have obtained a cost, an exact cost from the aggregate problem for the red states, we have to extend it to the black states, right? How do we do that? Well, there are a number of ways of doing it by some kind of relation or proximity. For example, black states that are close to a red state may take the value of the red state. Or otherwise, a red state right here may be obtain an approximate cost by interpolation of the approximate cost of the cost of the red states. One possibility is a nearest neighbor piecewise constant heuristic scheme, where a fine grid state, a black state, takes the cost value of the nearest coarse grid state. Okay, that will give you a piecewise constant approximation, right? And the levels are going to be the exact optimal cost of the red states. Okay, so that's the first idea, and we're going to build on that. So we'll introduce these representative states, and we're going to approximate the problem by projecting onto them. So look at this figure here. The black states are in this black enclosure, and they are the original states, okay, of the original problem. The red states are the representative states. It's just a subset, okay? And we're going to relate the original system states, like this J, to the aggregate states by means of some kind of a similarity or proximity coefficient. These phis here add up to 1. They are probabilities. They are weights that connect the original system states to the representative states. They are non-negative, and they add up to 1, okay? So in a problem that has a geometric character, this may be distances, okay? Or in a problem that has a different character, they can be selected on the basis of intuition of the given problem. You could also have only one of these phis be 1 and the others be 0, okay? And then you attach the black states to a particular representative state. Okay, so I have these red states, and I have introduced these aggregation probabilities, and this defines aggregation dynamics, whereby the transition probabilities between two representative states, like this X and this Y, generally speaking, I'll be using the convention, aggregate states are going to be X's and Y's. Original system states are going to be I's and J's. So from X to Y, what is the transition probability given these phis? Well, it's this one. It's the probability of going here, and the probability multiplied with the probability of going of this probability here. And we have to add, of course, over all possible successors of this representative state. Okay, let me repeat here. The black state, the red states are just legitimate states. They're just representative. The green arrows are the transition probabilities of the original system. And then we complete the transition to another representative state by using these aggregation probabilities. So this defines for me transition probabilities between representative states. In the process of this transition, we incur a cost. What is the cost? Well, along the green arcs, we have a certain cost, g's of x, u, and j, and depends on u. And if we average over all j that come out of this x, we obtain the expected cost from representative state x under control u. So my model is completely defined now. These are the transition probabilities given these phis, and these are the expected costs. And I'm in business with dynamic programming. Here's the aggregate problem. The original problem involves transitions and costs from i's to j's. The aggregate problem involves transitions from representative states to representative states under these transition probabilities and under these transition costs. I can solve this problem exactly, and let me call R stars of x the optimal cost of representative state x. Okay? Now, having done that, I obtain approximate cost for the original states, the j's, by interpolation with these phis. Now, in the case where the phis are either 0 or 1, then I have a piecewise constant approximation. Why is it piecewise constant? Because all the phis here are going to be zeros except for 1. That's going to be 1. And if you consider this set here of all j's for a given y, if you consider the set of all the j's that map onto that y, which I call the footprint of this representative state, then j tilde is constant on this set and takes the value r stars of y. Okay? So this is a small dynamic programming problem. It gives me these numbers here, and I use these numbers to obtain a piecewise uninterpolated cost function on the entire state space, which is piecewise constant in this special case, where all the phi's are either 0 or 1. Okay? So basically, that's the aggregation framework of representative states. And for another picture, now I'm considering again the simple case of piecewise constant, where all the phi's are either 0 or 1. The green function is J star, okay? On this axis are the states and the representative states. Now the states are the things that are in here. The representative states are just these, okay? Each representative state under this assumption here has a footprint, and the approximation is piecewise constant. Within each footprint, the level of constancy is the optimal cost of the corresponding representative state. Now, if we didn't have this case where J connects to a single X, if J connected to multiple X's, then this would not be piecewise linear. It would not be piecewise constant. It would be piecewise linear, okay? And sort of a similar approximation, perhaps a little bit more faithful, more ambitious to approximate well this green J star function. Okay, now for this case, there's an error bound. And this error bound is not important because you can calculate it and get some conclusion out of it, but because it is qualitatively expressive of what happens in these approximation schemes. So this gives you the approximation error for this case. And it says that let's consider these footprint sets over which the approximation is constant, and suppose that J star varies little within these sets, okay? Then the approximation is good in the sense that the error is small. So look at this bound here. If epsilon is the maximum variation of J over all these footprints, okay? So look at this particular footprint and look at states, look at the maximum variation within here, the maximum variation over all of those, and let's call this epsilon. Then J tilde produced by the aggregation scheme is within J star with a bound of epsilon, but divided by 1 minus alpha, which I don't particularly like. But the thing to read from this theorem is that the error is small if J star does not vary very much within this footprint. In fact, if J star did not vary over this footprint, if the original green function were piecewise constant, exactly like that, then aggregation would nail it exactly, would find the exact J star. There are bounds like that all over the place in the theory of aggregation. And again, you should not look at them literally. You should look at them more from the point of view of what they express qualitatively. Are there any questions about the framework so far? Let me stop the video here and ask for questions. Are there any questions? Okay. Remember our terminology and notation. I's and J's are for original system states. X and Y's are for aggregate states. We have representative states in this framework. We have this aggregation coefficients that connect J's with Y's, okay? And the approximate cost function produced by aggregation is obtained by interpolation of the exact of the R stars that are obtained by solving the exact aggregate problem. Okay. So how do we solve this aggregate problem? This is my aggregate problem here. I have defined its transition probabilities. I have defined its cost function. And I can use any exact method. If I can calculate all these numbers, I can use any exact method for solving the problem. Value iteration, policy iteration, optimistic policy iteration, linear programming, whatever you might have. The problem is a little bit more difficult, perhaps, because it involves these extra probabilities here. And notice that the problem is stochastic. Even if the original problem is deterministic, the aggregate problem is stochastic. Okay? However, there is some problem here. Do you see the problem? Potentially for large, if n is large, suppose that n is large. What's the potential difficulty here? Suppose n is 10 to the 100, let's say. There's a summation here over n. If n is very large, you would never make it unless the problem is sparse, okay? I have relatively few x's, and I have only few successors, j, okay? Then I'm lucky I can use this method here. Otherwise, I will need to have some different way to deal with this problem, and the way to deal with it is with simulation. If I have a simulator for the original problem, then I immediately get a simulator for the aggregate problem because my fees are given. So all I have to do is concatenate the system transitions with the fees, and I get a simulator for the aggregate problem. So I can use this simulator to obtain an exact model-free method based on the simulation. Notice here the use of the term model-free. I intentionally stayed away from using a sort of colloquial use of the term model-free. Model-free does not mean that you have for our purposes, model-free means that you're using simulation. It doesn't mean that you don't have a model. Here we may have a model, but we may use a model-free method anyway, okay? Okay, so really that's all there is to say about this representative states model, because we have a solution method and we have a variety of stuff here that we can use. If the number of x's is very large, you may consider using an approximate dynamic programming method to solve the aggregate problem. Okay, it's also possible to do that, although we're not going to emphasize this possibility. Okay, now if you think back at the framework, you'll see that everything applies to the case where the state space is continuous. Okay, think of a continuous state space and get a finite number of representative states in there. If you can calculate the corresponding transition probabilities and corresponding costs, you have an approximation to the original continuous space problem. We haven't talked about infinite horizon continuous space problems except in the very beginning. There is a theoretical requirement that the cost per stage should be bounded in order for the theory, the good theory, to apply, because only then we would have contraction mappings underlying. But that's fine, okay. The cost per stage should be bounded. We can still use a simulation based approach for solving the aggregate problem, because if we have a simulator for the original continuous space problem, we still have a simulator for the aggregate problem as well. So in this way, we have a general discretization method for continuous spaces discounted problems. And this can be quite useful in a number of contexts. And an important context where this is true is POMDP. Now, POMDP, remember, is finite state problems with partial state information. And
one way to address them is to consider the problem in the belief space of probability distributions of the state given the information. So in belief state land, you have a dynamic programming problem that has a continuous state space, because the space of probability distribution is continuous. However, this type of problem fits neatly into this formulation here. All we have to do is introduce representative states within the simplex of belief states, and then solve the corresponding MDP. So the partial observation is lost within this framework. We have a regular plain vanilla Markovian decision problem with perfect state information. It has a finite number of states, finite number of controls, because the POMDP is assumed to have a finite number of controls. And it can be easily defined and can be solved by any exact model-based or model-free method. And after we solve this discretized POMDP problem for the optimal aggregate called R star, then we obtain an interpolated approximate cost function. That's a powerful method, actually, to solve POMDP with relatively few states. That people don't, it has been addressed in the literature for quite some time, but people don't like it very much. They look at other methods, whereas very often this type of method applies very nicely. Okay, so I have a challenge question for you involving continuous spaces problems. I have a self-driving car that wants to drive from point A to point B within this continuous space. And it has to avoid these red obstacles here. And it has a travel speed of 1 meter per second, but in any direction. You can point the car in any direction you want, and that's its travel speed. And this is 1,000 meters, and this is 1,000 meters. Okay, so this is a problem that has it's a shortest path problem, but with a continuous state space. So I approximate this by introducing a fine grid, okay? Makes sense to do that. And, okay, we discretize a space with a fine squared grid, and we restrict, in order to stay on the grid, we restrict directions of motion to be horizontal and vertical. So in this approximation, it has to move on the grid at this speed here, but go one step horizontally or one step vertically. So we restrict also the direction of motion, not only the direction of the endpoints at each step. And then we solve this by a shortest path method, right? And we take this solution as an approximation to the solution of this problem. Is this a good approximation? Okay. I want you to think for 5 minutes. Some of you may know the answer, so don't give it away.
Okay, guys, let's take a 5-minute break for you to think at this question. It's sort of a cute question because, particularly because it involves a pitfall that many people fall for. Even experienced people make mistakes around this question. So what I'd like you to do is take 5 minutes to look at this question. We'll come back and also take the opportunity for you to ask questions about the slides so far, the approximation, the aggregation with. Okay, so we will take 5 minutes break, and we'll take 2 breaks in this lecture. And we'll come back in 5 minutes, and you may give some thought to this question and also think about other questions that you may want to ask about other aspects of aggregation that we have presented. So we'll meet in 5 minutes. Okay, we are back now. So let me ask first whether there are some questions on the earlier part of this presentation. Okay, so we will address this challenge question now.
Let me explain this a little more. Okay, the discrimination is flawed, and here's an example. That assume that all motion costs 1 per meter, okay? And there are no obstacles. Then the continuous optimal solution is the straight A to B line. There are no obstacles here. And it has length. It has length square root of 2 kilometers, right? It's 1 kilometer this way, 1 kilometer this way. Around the hypotenuse is square root of 2 length. And this is the optimal cost, the optimal distance, okay, from here to here. However, the discrete optimal solution involves counting units along this piecewise horizontal vertical path, and no matter how you do it, you're going to have a distance of 1 and another distance of 1, 2 kilometers, okay? Not a square root of 2, 2, no matter how fine you make the discretization. And the problem here is that the state space is discretized finely, but the control space is not. Okay, you have to discretize the control space also, many directions, and then use aggregation, okay? Use a stochastic formulation to make interpolations appropriately, and then in the limit, you can prove that you can get the optimal cost. Yeah?
So if in the action space, I would have allowed that I can move from one corner to the other corner, would that improve the whole solution then? So if I have an action space, so you are considering only horizontal and vertical. If I also consider an action that I can go diagonally from one corner to another corner.
No, it will not work. What you're saying, if I understand it correctly, is that suppose that here, not only you can go up or down, or you can also go diagonally. That will not work. The reason is that instead of having the control space, instead of discretizing with 4 points, you want to discretize with 8 points. But what we want is a large number of discretization points. You need to take all these diagonal directions and approximate with a finite number, a large number, and then you would be getting the optimal cost in the limit. Yeah.
But that would improve it, right? The 8 points would improve it.
8 points will improve it, yeah. But instead of a square root to 2 bound, you have a different bound, a little better bound, okay? But still, you have a problem.
But what if that's good enough? What if 8 points is good enough?
What you can say mathematically is that if you add more and more directions, diagonal directions along which you can go, in the limit, you're going to get the optimal. That's
And that also increases the number of states that you have, right? For each new action that you add. Well, if you add 8, it doesn't increase.
it will not increase it, okay? It will not increase it because you'll keep those black states to be the representative states, and then you'll add aggregation coefficients. So you move perhaps from here and you end up somewhere in the middle of the square. And then with aggregation coefficients, you interpolate to the neighboring black states. So to solve this problem, to solve this continuous space shortest path problem, you need to make it stochastic. You need to make it a stochastic shortest path problem to solve it by aggregation. It's an interesting concept. In order to get the exact solution in the limit by discretization, you need to pass to a stochastic formulation. Now, in the POM-DP example that I gave earlier, this is not an issue because in POM-DP, the belief space is infinite, is continuous, but the control space is finite, still finite, okay? So we don't have this particular problem here. Okay.
Are there any questions about this discretization paradigm or counterexample? Okay.
So now, from aggregation with representative states, I'm going to pass into a broader and more powerful aggregation framework that will involve features. Now, what's the main difficulty with the representative states scheme? Well, it may not be easy to find a set of representative states and corresponding piecewise constant or linear functions that approximate well J star. If you do blind discretization, you can't figure out where the function changes by a lot or the J star changes by a lot or by a little. So some parts of the state space may need more representative states and others may need less. So if you go blind into a given problem, it's hard to find, it may be hard to find a good set of representative states. They may be too many, in other words. You may have to go to a very large number before you get into a good approximation of J star. Now, suppose you have a feature vector that you can trust. It sort of expresses the nonlinearities of J star well enough. Then, instead of discretizing the state space, we discretize the feature space. So we introduce representative features that span adequately the feature space, and we aim for an aggregate problem whose states are going to be representative features rather than representative states. And we associate every representative feature with a subset of states that relate to it approximately, that approximately map into that representative feature. Remember, X is a representative feature, and we consider states that have a feature map that almost map into that. And this relationship between states and their features and representative features is done with the help of some weights, which we call disaggregation probabilities. The disaggregation probabilities roughly say how close the state I is to the representative feature X. We also consider aggregation probabilities, interpolation coefficients, from passing from aggregate to original cost function. And we construct an aggregate problem using the representative features, the phi's, aggregation coefficient, and these additional coefficients that relate features with states. Okay. So here's the conceptual picture. Here's the state space, and this is the feature space. So these are features in here obtained by applying the feature extraction mapping, the F, onto these states here. We discretize this. A regular discretization in the feature space gives you an irregular partition of the original space, where i's of x are okay, we pick a state x inside here, which we consider a representative. And i's of x is the set of states that map into the neighborhood of x. So somehow we're able to look at the feature space, sort of partition it, discretize in some regular way, obtain the representative features inside each one of these, and look at states that map in the neighborhood of each one of these representative states, and we call them i's of x. And for these states here, I introduce a non-negative, a possibly positive coefficient d. So here's the figure that I had before, but enlarged somewhat. We have transitions from representative features to representative features, and from original states to original states. And we go this way, and we map representative features into a subset of states, like this one, which almost have feature value equal to x. And then we go back here, and we use these aggregation probabilities. And once I define these d coefficients, these probabilities, and these p's, I have a model for transition from one feature to another feature, and also a model for the cost, the corresponding cost. Now we have to explore the properties of this problem here, whether it's good or not, but this is the basic framework. Representative features plus connecting probabilities, connecting weights, connecting relations, if you will. Okay, so let's take another break just to give you some time to assimilate this concept a little bit, but I'm going to ask you the following question. Okay, this is the figure I had in the previous slide. Why is the representative states model a special case of the representative feature model? Now that's an easy question, just to warm you up, okay? And here's another question. Just like we had this error bound for representative states, there is a general principle in this feature-based aggregation, which I'm not going to prove right now, but it's intuitive, namely that we should be choosing features so that states with similar features have similar cost function. Okay. Makes sense. That's what features are for, to tell us something about J star, right? So suppose that we have a feature map like that. In other words, J star changes little within each of the footprint sets where these probabilities are positive. Can you think of examples of feature schemes that would fulfill this type of condition? What would be useful features to choose in this context here? Let's take just a few minutes to think about that, and then we'll come.
Okay, guys, I'm pausing the video. Let's take 5 minutes to sort of warm up to these questions and try to get used to the notation and the concepts. And then when we come back, you can ask your questions, and we can also continue with these questions. So 5 minutes, and we're coming back. Okay, we'll take 5 minutes. All this is very new, okay? It's very different than cost function approximations from data and fitting target functions with neural networks and least squares and things like that. So different, conceptually different. It's not difficult, but it's different. So I'll give you another 5 minutes to sort of browse through the formulas and the notation. And we will come back in 5 minutes. Okay, let us come back to these questions of what would be useful features for aggregation purposes. Are there any questions at this point that you want to ask? Okay. And I want to ask whether there are any questions so far before we go into this question 1 and 2.
Yeah, can we extend this? We can extend this to a Q-learning setup, right? Where we would just use the aggregate state in place of the original state. So in regards to like the state action pairs that we would use in Q-learning.
Yes, it's possible to use Q-learning for the aggregate problem. So the state action pairs would correspond to aggregate state and action pair. It's not so simple as it sounds, but it's a possibility because there are fewer state action pairs in the aggregate problem.
Right, yeah,
But
that's
we're
what
not going to get into that.
Okay.
We're not going.
Sure.
We're going to get into some other methods that are simulation-based, but not Q-learning.
And then are we also going to get into, I think it lends itself obviously to some parallelization. Are we going to be talking about that later? Or if not, could you just maybe give an overview of that?
I'm not sure there are interesting issues that are specific to aggregation. There are generic parallelization issues that apply also to aggregation, but no specific issues that have that exploit the aggregate structure. I don't think.
Okay.
Okay, so let me restart the video.
Convene again. You know the answer. Okay, so let me get into that. Examples, feature-based aggregation. Okay, use a scoring function, okay? Suppose you have some kind of a scoring function, V, which is approximate J star. Then we can group together states with similar scores and call these sets features, okay? Within which set does your state fall? In particular, we can partition the range of values of V into M disjoint intervals, like what you were saying earlier. So, okay, so let's look at this figure. It's a little complicated. The green function is J star, but we're trying to approximate. The red function is what we're going to get. The black function is the scoring function. It doesn't have to be very close to the green function as long as it catches the rises and falls, the shape of J star. So now we look at the range of the scoring function, which is from here to here, okay? And then we cut it into pieces. And the corresponding states we call the footprints of feature, representative features. So a representative feature would be the middle point, let's say, of this interval that corresponds to the topmost range. Another representative state feature would be here, here, and so on. And so we define a feature vector according to this, which says if your score is within this interval, your representative, your feature is the index of that interval. Okay. So the feature here is membership within the corresponding interval of the scoring range. Okay, so this is one idea. And how would I get good scoring functions? Well, cost functions of heuristics or policies, we mentioned that. Approximate cost functions produced by neural networks, perhaps after one or two policy iterations. Now let's draw a connection with rollout. In rollout, what we do is we have a policy and we evaluate its cost. Now suppose we take a scoring function, the cost of a policy. Then rollout produces uses as cost approximation this J mu and aspires to do better than this J mu. Now suppose I use J mu as my scoring function to form features. Then the resulting J tilde is not J mu, but it's a nonlinear function of J mu that aims to approximate J star. In other words, aggregation goes for J star, not for an improvement of J mu. You see the difference? It has the potential to give you much more than the rollout approach. In fact, if the scoring function quantization were so fine as to have a single feature value per interval, then I would have J tilde exactly equal to J star. Okay? If I discretize my feature range finely enough, then I will get J star, not an improvement to J mu like rollout. I will get J star, which is much better. So with this type of scoring function, you can view aggregation as a more sophisticated form of rollout. The downside to this is that it's more computation intensive, because if you have J mu, then rollout can be implemented very easily, just one step look ahead. It can be done online. However, here there's a lot more computation to be done to solve the aggregate problem. Using a single scoring function can be enhanced considerably by considering multiple scoring functions. Okay, so if one scoring function doesn't catch it, you get some differentiation of features through another scoring function. Okay, so let me get into the possibility of using neural networks. And this is the big thing about neural networks. Out there at the output, it produces features and produces some kind of a cost approximation by linear combination of these features. So suppose that we have trained a neural network, maybe with one or more policy iterations, and we have obtained an approximation. These features now can be used by discretization to form representative features. In other words, we can sample this feature space that we obtain from the neural network, and in fact, the training process of the neural network produces a lot of feature values, right? In fact, state feature pairs. So we can obtain representative features and footprints corresponding footprints of corresponding states from the training set of this neural network, and we can perhaps supplement it with additional pair data, perhaps to improve exploration, for instance, things like that. Moreover, I can extend the set of features that I get from a neural network by using some handcrafted features in a more sophisticated and ambitious formulation. And notice now that this form of aggregation yields a nonlinear function J tilde of the features. This is linear. The aggregation will give you a nonlinear function that aspires to approximate J star, not J hat. So it goes for a bigger target. Okay. So now let's look how policy iteration would look in the context of aggregation and neural networks. Suppose I use a neural network-based parametric approximation to do policy iteration. We have gone through this. We have a scheme that generates a sequence of policies, and from the current policy, we train a neural network to represent the cost function of that policy. How do we do that? The neural network generates a feature vector, linearly weights it, and obtains an approximation to J nu, the cost function of mu. And then we do a policy improvement operation, a one-step look ahead, and I obtain the improved policy. This is what we have gone through with a neural network. Now suppose I bring in aggregation into this picture. How would it work? Again, I want to generate a sequence of policies. From the current policy, I have the neural network producing a feature vector, but instead of using this feature vector to obtain an approximate cost function, I sample this feature vector for representative values, for representative features. And I obtain an aggregation framework which I can solve to obtain a new policy from the aggregation problem. This is going to be different than that and potentially more powerful. So there are several options for implementing this scheme. It's sort of a mixed neural network aggregation-based policy iteration. I can do this neural network process multiple times, each time followed by an aggregate problem solution, and that constrains a new policy. In other words, use this policy after policy after policy. Another possibility is to use the neural network training process and the feature construction only once, okay? And then obtain some set of features which I can use in the aggregation framework. I can also add, after the neural network feature formation, I can add problem-specific handcrafted features. I can add features from previous cycles. I can enrich my set of features in a more flexible way than otherwise. And one more thing about deep neural networks. Deep neural networks use more sophisticated final features and relatively fewer, okay? Because the training and the weights go through so many processes that at the end, you have at the end of a hierarchy of features, you obtain more sophisticated features, which can be more useful in the context of aggregation. You will need fewer representative states if you have better features, which deep neural networks will give you. Now, all of this is somewhat speculative. And those of you that have attended my lecture here at ASU at the end of April, end of last April, may remember the flavor of this line of development. This is relatively new. It has not been tested extensively, okay? But I hope that some of you will not do this for a project in 2 weeks, but will do it sometime in the next few months. May be interested in trying some of these ideas, because I think they do have merit. And like everything else in approximate dynamic programming, don't expect this to work well in every circumstance, but there will be, I'm confident, circumstances where it will do better than other schemes. Okay, there's a big omission so far. We have discussed how to solve the aggregate problem for the case of representative states, but not for the case of representative features. And this is an interesting challenge. How do we solve this aggregate problem, and how do we formulate it? The simplest thing to do would be just to mimic the simpler representative states model. In other words, okay, what are the transition probabilities from here to here? Well, there's a certain formula that corresponds to a given U for each pair x, y, okay? Okay, this is just the multiplication rule of probabilities. To go from x to y, I have to go to one of the states I with these probabilities here, and then go across with these transition probabilities, and then go down with these other probabilities, and this is what you get. At the same time, as I go through the cycle here, I incur a cost right here, right at this point. And that cost is the expected cost of going to states in here, and then the expected cost of making the transition. This down transition does not cost anything. So this is the expected cost per stage. However, this gives you a legitimate aggregate problem, but it is flawed. Can you tell why it might be flawed? These transition probabilities assign a U to all the states that correspond to X, okay? There's a big restriction on U here that's associated with transition from X transition from X. So it doesn't capture the variation of the control within the footprint states that this aggregate state maps into. It gives you legitimate J tilde, okay? But it is not very good. That's the problem. So here's the flaw of this simple version of the aggregate problem. Implicit in the formulas for the aggregate dynamics and the aggregate cost function is that for each given representative feature X, it's the same control that's applied at all states I in the footprint. This is fine in the case of representative states because there's only one state corresponding to each representative state, but it breaks. But these formulas become flaky when you have the more general framework of representative features. So what happens here, this problem can be solved again by exact model-free, model-based methods to obtain corresponding costs for the representative states. However, the J tilde that you obtain may not be as good approximation to J star as you would like. It's legitimate, but the approximation may not be very good.
Okay, so we will stop here. and we will continue in 10 minutes. So let's take a 10-minute break. And at that time, you can ask your questions about earlier parts of the lecture, and we will also consider a more sophisticated version of the aggregate problem that also gives more accurate approximations to J star. So we'll get back in 10 minutes exactly. Okay, let us get started. Let me first give a summary of the lecture so far. It's a different kind of methodology, so it's worth taking a deep breath and summarize what we have done. We are looking at an offline training method, aggregation, and it's different than the neural network approximation architectures type of methodology that we have discussed so far. That's based on sampling and least squares, solution of least squares type problems. Aggregation is based on ideas of problem approximation. Basically, we approximate the original problem with a smaller aggregate problem that's presumably easier to solve in order to get some kind of a cost function approximation J tilde to use in online play. And we define the aggregate problem by means of aggregate states and aggregation and disaggregation probabilities. And we saw two different types of aggregate states, representative states, which is the easy case. Each aggregate state is itself each representative state is itself a single state of the original problem. And we also consider the more complicated case of where the aggregate states are representative features, and each representative feature is associated with a subset of states of the original problem, what we call the footprint of the representative feature. And we have seen one formulation of aggregate problem, which we argued is not very satisfactory, or perhaps does not give us as good results as we would have liked, because it assigns the same control to all the states within the footprint of each representative feature. So what we're going to do next is look at this more accurate version of an aggregate problem, which we call the enlarged aggregate problem. Are there any questions before I restart the video?
In order to bring in controls associated with states, we have to bring this into the aggregate model. And what we will do is we'll create an enlarged state space that would involve both the representative features and the original states and their transitions. So now, from these, I tripled the number of states. I have this is part of one component of the state space, this one other part of the component, and another part. And each one of those has an optimal cost associated with it, R star, and I call this J tilde 0, and I call this J tildes of 1. These are not the same because there's an in-between transition between the two. Okay, so now I have an enlarged problem. I have, of course, the full transition mechanism through this aggregation, disaggregation probabilities, and transition probabilities of the original problem. And I have Bellman equations. There's one Bellman equation for this cost, another Bellman equation for this cost, and another Bellman equation for this cost. The first one is this one, right? It's the weighted, it's the expected value of J tilde 0 weighted with the probabilities of the disaggregation probabilities. The second Bellman equation is the original Bellman equation of the system. And there's another Bellman equation going down. J tildes of 1 is an interpolated version of R star, with the interpolation coefficients being phi. So I've created a gigantic Bellman equation, bigger than what I started, but it turns out that it's still simple. And the reason is the following. If I take this J1 tilde and plug it in here, and then take the resulting J0 tilde and plug it in here, I eliminate J0 tilde and J1 tilde. And I end up with this equation. Okay? You see what I've done? Taking this, put it in here, taking this whole thing and put it in here, and I've obtained an equation that has on the right-hand side the R stars, has R star on both sides, and the J tilde zeros and J tildes of ones have been eliminated. So now I have a composite Bellman equation that involves only R star. It has some differences than the Bellman equations that you have seen before because it involves a minimization here, an expectation here, but it also involves another expectation on the outside. Okay? Still, it turns out that this Bellman equation has a unique solution for a discounted problem because this mapping turns out to be a contraction mapping. You can prove that it's a contraction mapping, it has a unique solution. And you can try to solve it in various ways. Okay. Before we go into solution methods, let me mention an error bound for representative states for the piecewise constant case, where the aggregation coefficients are 0 or 1. So the approximation J tildes of 1 is piecewise constant, okay? It's constant within each footprint. So for that case, consider these footprint sets corresponding to the representative features. The result basically says that the error between aggregate cost and optimal cost is small if J star varies little within each footprint. In other words, you get an approximation that's piecewise constant like that. If J star itself also varies very little within these footprint sets, then the approximation to the optimal cost is small. And here's the bound. If epsilon is the maximum variation of J star within each footprint set across representative features, then the error of the approximation scheme is epsilon over 1 minus alpha. It's an amplification factor 1 minus alpha. This is just a generalization of the bound I gave in the previous lecture for representative states, which is not a surprise because representative states is a special case for representative features. So the implication here is that you ought to choose representative features so that J star varies little over the footprint of X. And this is true for this piecewise constant case, but it's generally true in the aggregation schemes. Roughly true, although it's hard to write a precise result. So that gives you a guideline on which sort of supportive to what I mentioned earlier, that you should choose feature maps such that states with roughly equal J star have roughly equal features, and also that you should be choosing representative features so that their footprint, within their footprint, J star does not vary much. Okay. So now let's go into the solution of the aggregate problem. Okay, so here's the aggregate problem. This is the composite Bellman equation. R star on the left side should be equal to H of R star, which is the right-hand side of Bellman's equation here. And I want to solve this equation. And it is natural to use some form of value iteration. Now, value iteration would actually replace Rk plus 1 with H of Rk, right? That would be value iteration. And it would work. On the other hand, it's difficult to implement because there is an expectation here that bothers us. It is a legitimate algorithm and converges because H is a contraction, but it's difficult to calculate H of Rk because of this outer expectation, and so we're going to use sampling to approximate that. And once you use sampling, you need to introduce also a step size, whereby at each iteration, you compute an approximation to this h of rk, and then you move in the direction of that approximation with a step size gamma k that's diminishing. Okay, now all of this is not easy to digest because it involves difficult proofs and some insight in stochastic approximation methods that I understand that many of you may not quite have. But so this is something to look into as at some time later if you don't quite grasp the details here. Okay, so here's how this works. Instead of computing an expectation, we just sample this. We sample, and at the time k, we iterate for a single representative feature. We pick a representative feature at random, xk, update the cost estimate of that using this interpolation formula, and we keep all the others unchanged. Now, ik here, okay, we need an ik. Ik here is a sample from the footprint of xk. And it's selected according to the disaggregation probabilities. And this algorithm is solid. It has a convergence result that dates back to the mid-90s. If you choose gamma k to go to 0 at a rate of 1 over k, and some other technical conditions here, actually this is the main condition, gamma k should go to 0, and also the other condition is that each representative feature should be taken up for iteration infinitely often. Okay, you can't stop iterating on some x, right? So with these two, you get convergence to the unique solution R star. And this is sort of reminiscent also of Q-learning. In Q-learning, we also had expectation of minimization. The minimization was inside an expectation, and we did sampling. You sample the outer expectation. This is very similar, and the proof of convergence is somewhat similar to Q-learning proofs. All of these proofs were done in the 90s. Okay, now this algorithm is still quite formidable because you have an inner expectation. So if the problem is not deterministic, this may be a formidable computation. Okay. So policy iteration does not have this problem. Why is that? Because in policy iteration, we don't have this minimization during the policy evaluation. So I can sample both the outer expectation and the inner expectation. That's the difference. Okay, so I'm going to go through this and show you the formulas. And so this is a policy iteration for solving the aggregate problem. And it consists of cycles of policy evaluation and policy improvement. It generates at each iteration a policy and also the aggregate cost corresponding to that policy. Okay? And these R's converge monotonically. There's no oscillation stuff here. It's all go monotonic, and in a finite number of iterations, Rk is equal to R star. Essentially, what you're doing here is exact policy iteration for the aggregate problem. There are no approximations involved here, and there are no oscillations, exploration issues, all this other stuff that can go wrong. Here, everything is guaranteed theoretically to work well. So let me give you the policy evaluation and the policy improvement cycles here. So we have a policy nu k. This is a policy that connects the upper transitions from original system state to original system state. And the policy associates each state to a control, right? Each state I to a control. Not a representative feature, but each state I. So the policy evaluation, we have the policy nu k, and we solve the corresponding composite Bellman equation. This composite Bellman equation, I've written here in shorthand, R sub x should be equal to this right-hand side. And notice now this right-hand side does not involve a minimization. It involves the aggregation, disaggregation probabilities. It involves the transition probabilities of the policy, okay? And it involves also the aggregation probabilities here. And so how do I solve this policy evaluation problem? Well, I can use a sample version of value iteration, the one that I had before, but we can do sampling for both I and for j. Okay, we can sample this probability, this composite probability here. And so that facilitates a Monte Carlo policy evaluation. But there's also an alternative. Look at this equation, okay? Rk is on this side and Rk over here. It is a linear matrix equation, right? And it can be written in this form, where Rk appears on the right-hand side, left-hand side, Rk appears on the left-hand side with linear coefficients that I collect in a matrix AK. And these coefficients are these things here times that, okay? These multiply the components of the vector Rk. And there's also a constant vector. The components of the constant vector are just this part. There's one for each x. And this is the vector bk. So now these are expected values that I can compute by Monte Carlo simulation. In other words, for every x, I can compute this thing here by Monte Carlo simulation. I get one entry, then a second entry. All the entries of bk can be computed separately and in parallel by Monte Carlo simulation. Similarly, the coefficients of this matrix AK can be computed in parallel by Monte Carlo simulation by doing this probabilities. Then, after I have calculated this to a degree of accuracy, I can use matrix inversion to obtain this solution. I make it sound easy, but in fact it's quite formidable. And here's one of the difficulties. There's an inversion here, and there's noise in the evaluation of this AK. Inversion does not like round-off noise or any noise, okay? It can wreak havoc. If you have a discount factor that's close to 1, then this count factor is related to the spectral radius of this matrix. In other words, the eigenvalues of this matrix is one eigenvalue set right up to 1, okay? It's equal to alpha. If alpha is very close to 1, you have to do a lot of simulation to get this AK accurately enough in order for this inversion to make sense. And there are special methods for inverting this type of method that try to circumvent around this problem of instability due to Monte Carlo noise. Okay, I don't want to get into that, but I don't want you to think that this is trivial. It's not. So this is the policy evaluation phase of the current policy, and we have to do policy improvement. And policy improvement is done in the usual way by one step look ahead. I have the solution. I have RK from the policy evaluation. I plug it into the usual policy improvement equation, and I obtain a new policy. Notice that there's an expectation here that will potentially bother us for some problems. You may have to use approximation in policy space on top of approximation in value space. In other words, calculate samples of this right-hand side and fit some policy using some kind of a neural network or approximation architecture. Nothing is easy in this field, okay? But we have, in principle, a certain method that has some nice properties, and we can work with it. Okay, so we have covered, that's all I wanted to say about simulation-based solution of the aggregate problem. Now let's talk about variations of aggregation. There's something called biased aggregation. And it deals with the following situation. Suppose you have already a good approximation of J star. Aggregation aims to approximate J star, but if you have already a good approximation, you may want to build on the approximation and correct the approximation V rather than start from scratch. Standard aggregation, the way I have presented it, corresponds to V equals 0, okay? Now, J star is this green curve here. This is the state. This is a function of the state, very oversimplified, an oversimplified picture. And V equals 0, you can set up the aggregation, corresponding aggregation framework the way I have described it, and obtain something like this red approximation. Now, suppose you know V that is sort of captures the shape of J star, more or less, then you may consider to use aggregation to build a correction. Now, aggregation is going to give you a correction to this V that will approximate J star. And how do you do this? You can do it very simply, actually, by modifying the cost structure of the aggregate problem to add this V in the up transitions and this V in the down transitions. Now, with this trick, the structure is modified so that J tilde gives you V plus the interpolated R star. Okay. Now, this is not so, this takes a little, it's easy to see, but you need to write it down to convince yourself that I've done the right things here. I have added and subtracted the proper amounts. This is actually, in reinforcement learning, this process is also called cost shaping. You may have seen this. Cost shaping or reward shaping. It's actually an old technique in dynamic programming that dates back maybe 30, 40 years. When people try to modify the Bellman equation by adding and subtracting quantities and put it in some kind of variational form. But in the modern days, you may see it as cost shaping. And given this V, and given this aggregate framework, including the enlarged state space, but just a different cost structure, then you will have three Bellman equations giving you R star, J tilde, and J tilde 1, J tilde 0 and J tilde 1. And note that because of the presence of V, J tildes of 1 is going to be V plus a correction, okay? This is the correction that we add to V in order to get an approximation to J star. If you know V to be, if you know J star itself and you stick it in here, then you're going to get R tilde 0, J tilde 0, and J tilde 1 equal to J star. And the aggregation framework is going to give you the optimal policy for the original problem, okay? So this suggests that if you know a V that's close to J star, the aggregation problem is going to give you a better result, a good result. Suppose you have some policy and you choose V to be the cost function of that policy, then you can apply this aggregation framework, and then you get something that looks like a rollout. In fact, if you have a single representative feature that maps to all the states here, it's going to be exactly the rollout algorithm. And this suggests that if you have multiple representative features, and therefore a more accurate approximation framework, then the aggregation policy is going to be much better than rollout. All of this has to be verified, but it's clear from simple examples that this should be true in some form. All of this is very new, okay? We're talking about stuff that's been developed in the last 3 months. Okay, there are error bounds also, similar to the case where V is equal to 0, and suggest that once you choose representative features and footprint sets, so that within which V minus J star varies little. Not just J star, but V minus J star. Now, okay, I'd like to use V minus J star to construct representative features, but I do not know J star. So one possibility is to use k-value iterations on V to approximate J star. That will give me roughly the shape of this difference, which is what I need to know actually for picking the representative features by using this expression as a scoring function. I'm rushing all this by you, but you may want to look at all this later. It does make sense, but you need to look into it a little bit more deeply. So that's all I want to say about bias aggregation. It looks like a promising idea, but at present has not been tested extensively. The idea of using cost shaping has been tested in reinforcement learning with results that look good, but not fully convincing to me. Okay, but it's something that people have looked into.
Okay. By the way, this lecture was videotaped in 2019. So the biased aggregation result and some of the earlier ideas in the lecture were very new at the time that they were presented, but now it's been like 3 years, 3 years that have passed. Still, the subject is unexplored, and I hope that some of you will be interested to take a closer look, because I think they're interesting ideas that may be very uniquely well suited for particular application contexts. Are there any questions? I have a short video for another variant of aggregation, and I'm going to go to that.
So now let's look at another version of multi-step look ahead. You remember we had an aggregate problem structure involving representative features, transitions to the original system states according to the disaggregation probabilities, one transition to a system state, J, from I to J according to this transition probability, and then go down to an aggregate feature using disaggregation probabilities. Suppose now that instead of a single transition before going down, I use n transitions. What would be the benefit of that? What would be the benefit of using this multi-stage structure versus using the structure where n is equal to 1? Well, this problem may be a better approximation, right? It's more faithful to the original problem. The original problem is an infinite number of green transitions, right? So here we're going to take a large number of transitions potentially in between, dropping down to the aggregate states, making some kind of compression of the state space every n stages. So we hope that this framework will be more faithful to the original problem. However, now we have an enlarged state space that's like that. And it involves n plus 2 stochastic Bellman equations. Value iteration based on sampling goes out the boards, okay? You can't do it. Why? Because there's a minimization over minimization over minimization over minimization, each time involving an expectation in between, so it just cannot be implemented. You can implement policy iteration because for a given policy, this transitions here, you can do Monte Carlo. There's no minimization, so you can do Monte Carlo across these transitions. However, the policies that we implement are multi-step, okay? They're not just a single-step policy, but end-stage policies. So that complicates things for a general stochastic problem. Now here's a simpler case that I'm going to focus on. A deterministic problem in the representative states, no features, okay? So from representative state, I go to a true system state, to the same, I stay at the same state, and then I move deterministically across. I end up with, at some, after the end of n stages, at some original system state, which I interpolate with a phase and go down to the representative features here. Okay, so now value iteration involves the solution of an n-stage deterministic problem. There is a minimization across the stages, but this is deterministic. So that means a shortest path calculation over the n stages. And basically what you're solving is an n-stage Bellman equation, I'm sorry, n-stage value iteration type of equation involving n stages of the dynamic programming operator. So value iteration would take this form, and this would involve minimizations in between, but these minimizations are solvable by shortest path calculations. So now if you look at this algorithm here, it involves aggregation in space, because I'm looking at a small subset of states, the representative states, but also it involves aggregation in time. I'm aggregating one transition from X to Y I'm aggregating n stages, n time steps into a single transition from X to Y.
Okay, there is the 2019 lecture has a lot more material on aggregation in both space and time. It's an interesting subject that has not been explored fully, but we're not going to get to this because it becomes too technical. So we will now, we have now finished the technical part of this lecture, and also of the course, by the way, because our last lecture, we have only one lecture left. And in this lecture, we will do an overview of the entire course. And you can bring your questions from any part of the course at that overview. And however, the new material, there will be no new material. All the material of the course has been covered. Okay, so we'll see you next week for the last lecture, which will be an overview.